Hello, this is Mrs. Huntley. This is Module 5, Lesson 2, a formal definition of a function. Your essential question for this lesson is what is a function? And it would be a really good idea if you had a calculator and a highlighter for this session. If you remember, in session 1, we talked about what a function was, and we said it's a predictive relationship, that we use functions to predict outcomes between two variables. So a formal definition could be that, and you can put this in your own words, because if you wouldn't say it's a predictive relationship, if you'd say more it's a relationship that you use to predict things, that's fine. Put it in your own words that make sense to you. What does that mean? It's a relationship between two variables that you use to predict outcomes. We actually started doing this in Module 4 when we were doing our application problems. Now, we didn't get too deep in the application problems because I knew that this section was coming, and we're actually going to be continuing with all of the skills that we learned in Module 4, and we're going to be applying them to new situations in Module 5. So, a function is a rule or an equation that assigns each input to exactly one output. So let's take a look at these tables before we answer this question here. The table on the left here is the table from lesson 1. That's example 2. Remember, this is when the ball or the stone, whatever it was being dropped off the top of the building, and it took exactly 4 seconds to hit the ground, which was 256 feet down. So these are the distance that it traveled at each time interval, and let's take a look if we can use this information to help us predict things. So we look at our inputs and we look at our outputs. Each input, is our x's. Each input is unique, meaning that we don't have the same number twice here. We've got 0.5, 1, 1.52, 2.53, 3.54. All of them are unique. There's no repeats. Let's look at the table at the right. We've got 0.5, we've got 1, we've got 1 again, we've got 2, we've got 2.5, we have 3, we have 3 again, we have 4. All right, well, let's take a look at which table would be the better table to use if we want to make a prediction. Say these are both data from somebody doing that ball drop experiment. And I wanted to know how far the ball was going to drop at 1 second. If I look at this table, I'd say, okay, at 1 second, that ball was going to drop 16 feet. I know pretty clear cut how far I would expect a ball or whatever I'm dropping off the building to be dropping in the first second. If I'm looking at this table and I say, how far in 1 second is this object going to travel? And I could say, well, maybe 4 feet, maybe 36 feet. Not exactly sure because the data is kind of all over the place. So I'm just going to highlight really quick because I want you to see what I'm looking at. I'm going to highlight in pink. At 1 second, it might be 4 feet or it might be 36 feet. Not really sure here. And then if I want to know at 3 seconds, if I'm using this table on the left, okay, 1 second, I know it's going to be 16 feet. If I'm using the table on the left and I say, how far is it going to drop in 3 seconds? I can say with some certainty, it's going to be 144 feet. If I use the table on the right, again, 3 seconds at 99 or 3 seconds at 196. So it's going to be somewhere between those distances. Which table would I use to make an accurate prediction? Exactly, the table with only one output for every input. So each input has to have one and only one output. Here we have an input or an x of 1 twice, and it's assigned to 2 different numbers. That doesn't make any sense. I can't use that table to be able to predict anything with any accuracy. So the table on the left assigns one output value, those are our y values, to each unique input value. That's our x value. So the inputs are our x's, the outputs are our y's. The table on the right has several different outputs assigned to the same input values, and we've highlighted them. Now I purposely highlighted in green over here, like green is go, green is good, green is a function. This pink, this hot pink, or I was going for red, but I didn't have red, but this pink would indicate this data is not necessarily wrong. It might have been real data that was collected. It's just not a function, meaning I can't use this data to help me predict anything with any level of accuracy. So I'm just going to, excuse me, write a note. This table is not a function. Again, it's not wrong. It might be real data, but it's not a function. Can't use it to predict. Okay, can't use it to predict anything. So here's some new language or new ways of looking at things. So we're going to use the table that is a function to fill in this table down below. And it's talking about assigning our output to specific input. So I'm looking, they're giving us our output. Our output is 4. The function D, they're calling it a function D, assigns 4 to what input? It would be an input of 0.5. So the output is assigned to something specific. 16 would be assigned to 1. 36 assigned to 1.5, and so forth. Go ahead, don't wait for me. Just go ahead and fill out the rest of the table. Oops, I just did that wrong. I hope you didn't follow me. I was looking at something and not focusing. Okay, so 256 is assigned to 4. So the way I would say this is just like I'm reading it. So D, the function D assigns 64 to 2, or the function D assigns 100 to 2.5, etc. And 44 to 3. Where am I getting the values? I'm just reading the table backward. The output is assigned to some specific input. So you don't have to write this next part down, but this is something that we actually mentioned. We've been talking about inputs and outputs. Back in elementary school, we learned different mathematical functions with input-output machines. Maybe we learned how to add or subtract. And does this look familiar to anybody? Perhaps we had certain numbers that were being input into our little machine, and the machine rule was +3, and our output would be whatever we put in +3, and comes out the machine. If you didn't do this when you were in elementary school, that's okay. That's not a problem. We're going to be talking about input-output machines just a little bit. And, hopefully you're making a connection to back in elementary school when you were learning different math functions. So we're going to use the input-output machine to try to come up with a way of describing the oh my gosh, I just lost my train of thought completely. We're going to use our input-output machine example to try to talk about the example with the dropping ball and see what we come up with. So what would our input be? Our input is going to be the time interval. Okay, so with the example we've been talking about with the rock dropping, the input is the time interval. The output would be the distance traveled in the given time interval. So when we input 3 into our machine, what is our output going to be? Well, if we look at the table, when our input was 3, our output was 144. That's how far that rock had dropped. Okay? If we input 1.5 into the machine, our output is going to be 36. Does that kind of sort of make sense? Now let's talk about limits real quick. The input is limited by the length of time it took the stone to drop and hit the ground, 0 to 4 seconds. Now that's called the range. This is actually something that you're going to have to learn this terminology when you're in high school, but why not go ahead and learn it now while we're learning about functions? So your inputs are the range. That's the numbers that we can put into our machine. The output is our domain. and it can be described as the function, rule, or the equation that defines the function. Again, those are just vocabulary things, putting new academic language on things that you already know. And I don't see, you're not going to be required to use those words here in 8th grade, but you are going to be required when you get to high school and you're talking about functions to know what the range and the domain are. So again, range, input, domain, output. Okay, we learned in the last module that a linear relationship can be shown in a lot of different forms. Tables, equations, graphs, and words. Functions are the same. They can be presented in all the same forms. And actually, our table that we've been using, our upright table, is now a flattened table. And again, there's no difference. It's just before we saw it as being stacked on top of each other, and our x's were on the left, our y's were on the right, and our data went down. Now our x's or our t's are on top and our y's are on the bottom. It's no different. It's just in a different format. So don't let that throw you. We determined that y was the distance traveled in time, and then the equation that we came up with to represent what was happening when the stone was dropping was y equals 16. We said x to the second power. They're saying t to the second power. I will leave it up to you if you want to change it. I kind of like x's and y's, but that's how my brain sees it, and maybe it's because that's how I've always done it. This is the first time that I think you're old enough to where you don't have to have the t's and the d's and stuff like that. Y equals 16x to the second power, or if you like the t, leave it as a t. But our t is our time. That's our input. That would be our range. So when I put 0.5 raised to the second power times 16, what's my output? And again, you could put this in your calculator a number of different ways. You can do 16 and then put a parenthesis, x to the second power, or 0.5 to the second power n parenthesis, and it will give you the correct answer. You can do, like I said, 0.5 to the second power times 16. The order that you put multiplication in doesn't really matter, and that is how my brain sees it, because my brain automatically uses the order of operations. So what I'd like you to do is grab your calculator and go ahead and put in 0.5 to the second power times 16. And what do you get? I got 4. Go ahead and do it with the rest of the table. So 1 to the second power, 1 times 1 is 1, times 16 is just going to be 16. Don't even need your calculator for that one. 1.5 to the second power times 16, going to be 36. 2 to the second power is 4 times 16 is going to be 64. 2.5 times to the second power times 16. Okay. Are the distances you calculated equal to the table from lesson 1? And yes, they are. We actually kind of derived the equation from that table in lesson 1, didn't we? Okay, does the function y equals 16 x to the second power or t to the second power accurately represent the distance the stone fell in a given time interval? In other words, does the function assign t to the correct distance? Explain. And yes, it does. The function accurately represents the distance the stone fell over the given time interval. Each computation using the function rule or the equation resulted in the correct distance. So what I'd like you to do is re-examine the definition that I gave you on page 9. And what I'd like you to do is think about the phrase of exactly one output. Why is that necessary to have in the definition? It absolutely is. The definition of a function must have that each input has exactly one output, but can you think of why? And what I would like you to do is go ahead and put it in your own words right in here. If you have to pause the video, by all means do that. I'm just going to say for functions to be useful, the information we get from the functions has to be useful. Therefore, if you have more than one output assigned to an input, it's very hard to use it to be predictive with any kind of accuracy. Okay, so now we're going to look at some tables, and we're going to try to determine if the tables are indeed functions. So let's take a look at them. Our inputs are on top here. They're calling them X. I would suggest the first thing you do is kind of look over your inputs and make sure that they're all unique numbers. Now I've got 1, 3, 5, oops, 5. Okay, so now what we need to do is see, is 5 assigned to different outputs? So I've got 5 to 19, 5 to 20. Okay, the input 5 has 2 different outputs, so this is not a function. Okay? It's not wrong. Perhaps this is data that represents something. It's just not a function. I won't be able to use this data to accurately predict what the outcome is going to be when my input is 5, because I don't know if it's going to be 19 or 20. The next one. Okay, how are you going to go about this is check the inputs. If they are all unique, meaning they're different numbers. If there are 2 inputs that are the same number, are they assigned to the same or to different outputs? So the next one, 0.5. My inputs, 0.5, 7, 7, oops, 7's assigned to 10, 7's assigned to 15. That means this is not a function. It tells me to explain, and I should have done this up here too because it said explain. So input 5, and the top one, is assigned to different outputs. Okay, so the next one, not a function, input 7 is assigned again, not wrong, just not a function. Okay, I would like you to pause the video and determine if this next one is a function. Okay, number 4 is a function. Each input is assigned to only one output. So I've got 10, 20, 50, 75, 90. They're all unique. They only have one output assigned to them. Now, if you look, we've got 2 outputs that are the same, but that's okay. It just means at 10, whatever the input is for 10, the output's 32, and at 20, the output's 32. That's okay. Maybe it's a flat line at this point. You know, it's not going anywhere, and then all of a sudden it goes up to 156. I don't know. I don't know what the data is representing. I know it's a function, though, because my inputs are all unique. Let's look at the next one. Okay. It takes Josephine 34 minutes to complete her homework assignment of 10 problems. If we assume that she works at a constant rate, can we describe the situation using a function? Sure we can. So how do we do these types of things? Remember, whatever we do, we put over our time. So if she's got 10 problems, we put it over our 34 minutes. So 10 over 34. 10 problems in 34 minutes. Now we can see that this slope could be reduced. And actually, I want to know how long it takes her to do one problem. So I'm going to say that it takes it for one problem. It takes her 3.4 minutes. Now, can we predict how many problems Josephine can complete in 25 minutes? We should be able to. So y equals our rate times our time. So x is going to be our time. X is time. and y is our total problems. So total problems is 134 times x. We're going to plug in 25. So y equals 1 over 3.4 times 25. So 1 times 25 is 25 divided by 3.4. I'm going to get a weird decimal, so I'm going to round that to about 7 problems. Okay, I already wrote the two linear equation, so sorry, I'm ahead on that one. Use the equation you wrote in part B as the formula for the function to complete the table. Round your answers to the hundredths place. Okay, I'm going to end the video here because I just looked at the clock and realized that I'm at 21 minutes, and I apologize for that. I did not realize that I had gone over. So we will finish parts C through F in class tomorrow. If you want to keep going and you understand what you're doing, by all means, keep going. Right now, I just want to wrap up the lesson. So the purpose of a function is to be predictive. A function is a rule or a formula that assigns each input to exactly one output. Not every function can be expressed as a mathematical rule or formula. The rule or formula can be a description of the assignments. Functions have limitations with respect to the situation that they describe, and functions are sometimes described as input-output machines. I hope you have a great night, and I'll see you in class tomorrow.